Okay.
So, hello everyone. My name is Rishi Agarwal and I'm from Team Archmages. Today I'll be presenting the paper Maya Falsifying Power Side Channels with Dynamic Control. The link to the paper is given below, and I would like to acknowledge that the figures for graphs and results have been taken from this paper. So, going ahead, imagine that Alice is using a computer and Eve is an evil attacker who can track the power consumption of Alice's computer. Now, just by measuring power, Eve can actually recover sensitive data like password length, keystroke, browser activity, camera activity, location, bits of encryption keys, and the application activity. So this is dangerous, right? And this is an example of how Eve can actually use the power measurements to find out which application was running on Alice's computer. So on this graph, you can see that the y-axis is the average power and the x-axis is the time steps. And the three plots that you can see correspond to three different applications: the Black-Scholes, BodyTrack, and Water and Squared. You can clearly see that the plots are distinct. You have distinct patterns for each of the three applications. And using the plots, you can actually identify which application might have been running on Alice's computer. Now, our goal is to reshape power so that the graph on the left is transformed to the graph on the right. And just by measuring power, Eve should not be able to find out which application was running on Alice's computer or any other sensitive data. Now, there has been some prior work on this, but most of them require new hardware, so they haven't been deployed yet. There is a line of work called the trusted execution environment, like the Intel SGX. However, that is ineffective in this scenario because they cannot contain physical side channels, right? The information which is leaked by the physical side channels cannot be contained in an environment. And finally, there is another line of work which basically tries to add noise to the power signal and tries to distort the power signal. But that is ineffective because attackers have used signal processing techniques and have actually recovered the true power signal even from the noised power signal. Now let's jump and understand what Maya is at a 10K fade view. So Maya consists of two components. One is the mask generator and the other is the controller. The task of the mask generator is to generate target power R. Now this is the target power to which the controller tries to reshape the total power that is emitted by the computer system. So understand that the computer system is emitting total power P and the controller is trying to reshape the total power P so that it is as close to the target power R as possible. Now to do so, the controller has several inputs. The three of them that I've listed are the DVFS, or the voltage and frequency level at which the computer system is operating. The second is the idle thread execution. So the controller can execute an idle thread on the computer system so that the power consumed reduces. And finally, the controller can also execute a balloon thread on the computer system, and this will ramp up the power consumed. Okay, so just summarizing the discussion, we have a mask generator which is generating the target power, a controller which is using these inputs to modify the total power P that is being emitted by the computer system. Now let's dive into the controller and understand what the controller looks like. So the controller is a state machine and it maintains an internal state which is denoted by capital S. Okay, and at every time step you have two possible inputs, capital R and capital P. Capital R is the target power, capital P is the measured power. Using the two inputs, you compute error at time step T. Now you update the internal state given by this equation, and using the state at time step T and the error at time step T, you also compute the action that has to be taken on the computer system. So this action could be the DVFS level or the idle thread execution or the execution of balloon program. Now you might have observed that we have used matrix multiplication in the controller. So at this point in time, I would like to introduce you to two possible attacks in this domain. One is called the conventional attack and the other is a specialized attack. So in conventional attacks,
Rishi, there is a question.
yeah,
Is the controller hardware or it's a software driven controller?
the software driven controller. So
Okay.
we'll use an OS thread to actually simulate the controller.
Okay. Yeah, go on.
Yeah. So at this point, I'm introducing you to two possible attacks. One is a conventional attack and a specialized attack. So in conventional attack, the attacker can measure power at coarse granular time intervals, which is, let's say, every 20 milliseconds. Now, this attack is easy to mount and it is most widely used. However, in specialized attacks, attacker can measure power in every 10 nanoseconds, right? And this is expensive and difficult to mount. However, there is utility of specialized attacks as well. Like it can be used to steal the bits of encryption keys. But we are using a matrix-based controller and that can respond only in microseconds. So it cannot be used for specialized environment and it can only be used for conventional environment. However, there's an alternative which the authors propose, which is to use a table-based controller. So you have a table of pre-computed values instead of doing matrix operations, you are just doing a table lookup. Uh, but 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 for the rest of the paper and for the rest of this presentation, we will not focus on specialized environment and restrict ourselves to conventional environment. Now you might wonder how good is this controller? So this is an illustration to show that the controller can actually control and reshape the power to the target power R. So on the left, you observe the power trace, the target power capital R. The y-axis is the average power in watts and the x-axis is the time steps. And on the right, you see the graph of the emitted power or the measured power capital P. And basically, okay, so this power was measured when an application was actually running on the computer. So it basically means that the controller was able to reshape the measured power to look close to the target power. Now coming to the mask generator.
Rishi, question.
Yeah.
Go back to previous slide. So what was the target requirement here, like in terms of the power distribution?
The target was this left plot.
No, but how do you get this target distribution? Like who?
Exactly. That will come to in the next part, which is the mask
Okay,
generator.
okay.
So coming to the mask generator. So for an effective mask generator, you basically need the mask to be able to hide information in both the frequency domain and the time domain. Namely, because an attacker can actually generate the power trace and use a Fourier transform to actually analyze the power trace in the frequency domain as well, right? So for an effective mask, the authors postulate that the mask should satisfy three properties. And I'll be listing down these three properties right now. So one property is that the mean and variance must change over the time domain. The other property is that the frequency domain curve must spread over a range of frequencies. Okay. And finally, the third property is that there must be some peaks in the frequency domain curve. Now, what is the philosophy behind having these requirements, right? So the first thing is that applications tend to show these properties in their power traces. Okay. Now, if you try to generate a mask which does not show these properties, then you are asking the controller to reshape it. Then you're asking the controller to basically make these properties disappear, right, from the power traces of the applications, and that cannot be done. Like you cannot ask a controller uh, to vanish the peaks from the frequency domain curve. And if that cannot be done, then basically you'll be leaking information by using an ineffective mask. So that's why we ask that if the mask does not exhibit these properties, then the controller will not be able to hide them. Now for the next two slides, I'll be discussing two candidate target distributions. One is the trivial constant mask. So on the left, you see the constant mask, the time domain for the constant mask. You see that the power is in watts on the y-axis and the time is in seconds on the x-axis, and the line is a straight line. And this is the frequency domain. So after applying Fourier transform, this is the plot that you get in the frequency domain. And you clearly see that it is zero for all the frequencies and there are no peaks, right? So it is not satisfying any of the three requirements. It has a constant mean and zero variance in the time domain, and it neither has any spread nor any peaks in the frequency domain. Now the second mask is a Gaussian sinusoidal mask, and this was exactly the mask which I had shown in one of the earlier slides. So in this mask, you see that the mean and the variance are actually varying in the time domain, and you also see some peaks, and you also see a spread of uh, frequencies in the frequency domain. So it is actually satisfying all three requirements. Now the authors actually listed down 5 possible target distributions, and they finally narrowed down to using the Gaussian sinusoid distribution because of it satisfying all the three properties. Now that we have discussed about the general framework of Maya, let's look at some of the assumptions, some of the key assumptions, and some of the key strengths of this framework. So one key assumption is that the attack allowed is a conventional attack, which is an attack in coarse granular time domain. And the second assumption is that the attackers can actually know the algorithm. Okay, so we can assume that the attacker knows how the power was reshaped and he can plan the attack accordingly. Finally, there's an assumption that the hardware or the privileged software which is being used to implement Maya is uncompromised. So in our case, since we are implementing in software, the OS scheduler, the DVFS interfaces, and some other interfaces have to be uncompromised. Finally, the strengths are that you are able to reshape power effectively, which will in turn mean that you are actually protecting from other physical side channels like temperature and EM leakage, since these physical side channels are also directly correlated to power. And the big strength is that software implementation for Maya is possible. So let's just quickly summarize our discussion so far. We discussed about a matrix-based controller, and the equations for the controller are shown on the slide. And finally, we discussed about the mask generator and how we narrowed down to Gaussian sinusoidal mask based on the 3 requirements which were listed down by the authors. Now for the next few slides, I'll actually go over the experimental setup and the implementation details, like how is this framework actually implemented on software. So the authors basically used operating system threads, and they implemented Maya on 2 machines, a consumer class machine and a server class machine. Both were multi-core machines. And there were 3 possible threads that could be executed on each of the logical cores at any point in time. One corresponds to the parallel benchmark. The other is an idle thread, which is used to reduce power. And the third thread is a balloon thread, which is used to ramp up power. And the balloon program basically consists of floating point array operations in a tight loop, in a for loop kind of thing. Now, the attackers use RAPL interface to measure power. And finally, the controller, the mask generator, and the balloon program, they are running as privileged processes. Okay. Now, how are the inputs actually given to the computer system, right? Till now, we have just looked at inputs in an abstract manner, but how do we set the DVFS level, or how do we execute the idle thread? So to do that, we use the following 3 interfaces. To set the DVFS level, we use an interface called the CPU FREC interface. To execute idle thread, we use Intel's power clamp interface. And finally, for execution of balloon program, we use an SHM file. Now let's look at how the controller is implemented. So to implement the controller, we basically needed 4 matrices, A, B, C, and D, which were used in the state update equation and the equation to compute the action. Now to get those matrices, you basically compute a dynamic model of the system. It will be a polynomial model of the system. We'll look at this in the next slide. And we also need 3 parameters. The 3 parameters are the input weights, the uncertainty guard band, and the output deviation bounds. These are like hyperparameters, and they have been set to these values by the authors. Now, once we have this dynamic model, and once we have these 3 parameters, the matrices A, B, C, and D are automatically generated from control theory. Now, to get this dynamic model of system, you basically need to train your model on real data. So what you do is you use a technique called system identification. You use a computer system, you run many applications on it, and you save the data of what was the power and what was the input level that you had given to the computer system. Now, based on that, you actually fit this polynomial model. So what this polynomial model is doing is you have y of t as the output power that is given by the computer system at time step t. And that is a function of the previous m time steps. So you have the power output in the previous m time steps, and you have the input that has been given, input meaning the DVFS level or the idle thread. That input has been given for previous n steps, including the current step. And AI and BI are basically coefficients of this m output, of these m outputs and these n inputs. And based on these, you actually predict what is y of t. Now, AI and BI are basically the model parameters of this dynamic model, and they are trained using least squares. So you just do least squares minimization. So coming to the mask generator, as we discussed, we are using a Gaussian sinusoidal mask, and the equation for the mask looks like this. R of t is given as offset plus amplitude times sine of 2 pi t by frequency plus a Gaussian distribution sampled with a mean of mu and variance of sigma. Now the parameters of this distribution are offset, amplitude, frequency, mu, and sigma, all the italicized symbols. Now, now these parameters are basically sampled at random from a range of values, and these range of values satisfy two constraints. One is that the maximum power that this R of t can take should be less than the thermal design power. So every machine has a maximum threshold beyond which the power should not go. So R of t should be always less than that thermal design power. And finally, the frequency, the parameter that is frequency, that should be less than half of the power sampling frequency. Otherwise, you won't be able to detect the distribution that you are sampling. Now, you basically, once you've sampled random values for these parameters, for the next n-hold number of samples, you for the next n-hold number of samples of R of t, you use the same parameter values. And once you've generated n-hold samples, you change your parameter values by again randomly sampling these parameters. So for the evaluation methodology, we basically try to train two ML models. Both are multi-layer perceptrons, and we use two types of training techniques to train these ML models. So one is where the attacker does not know what the algorithm is, what Maya is, and just collects training data. Training data consists of power traces, and it just collects these power traces and tries to train a classifier, which based on these power traces tries to predict which application was running on the computer. And the other attack is that you train on power traces with Maya being run on the computer. So let's say that Maya is running on the computer system, and then you are collecting power traces. So this is called an adaptive attack. And once you've trained these ML models, you try to compute the classification accuracy on the test set. So in the next two slides, I'll be presenting the confusion matrix, the confusion matrices for two masks. One is the constant mask and the other is the Gaussian sinusoidal mask. And this is the scenario where the data was collected without Maya. So on the x-axis you see the predicted label, and on the y-axis you see the true label. And the basic takeaway from this slide is that the accuracy actually drops from 92% to 12% in the case of constant mask, and 13% in the case of Gaussian sinusoidal mask. Now you might wonder that the constant mask is doing well, but let's come to the other scenario, which is the adaptive attack. In this scenario, we can see that the accuracy actually increases to 67% for constant mask, but it remains as low as 20% for the Gaussian sinusoidal mask, which means that the second mask is actually able to hide and it is effective even in the adaptive scenario, but the constant mask is not effective in the adaptive scenario. Now we'll visualize the power traces for three scenarios. One is where there was no Maya on the computer system. The second is where we have used constant mask. And the third is where we have used a Gaussian sinusoidal mask. So on the x-axis, you see the time steps, and on the y-axis, you see the average power in watts. So you basically see that the leftmost graph, which is the scenario where there was no Maya, the plots are very distinguishable, and you can easily find out which application might have been running on the computer. In the middle plot, you see that the controller has tried to bring the measured power to a constant level. However, uh, the three plots can still be distinguished somehow. Like, it's difficult, but they can still be distinguished. And in the third plot, you see that the three distributions are clearly overlapping with each other, and you cannot distinguish between them. So the takeaway is that Maya reshapes power in application transparent manner, and the constant mask is less effective than the Gaussian sinusoidal mask. Now that we have looked at how Maya is on the security side, let's evaluate its impact on performance. There are some overheads on the performance side. So on this slide, I'll be showing you what is the impact of Maya on the power consumption. So the y-axis is the normalized power, and the x-axis is the different applications on which which were running on the computer system when the power was measured. So on an average, you see that the power consumed by the three scenarios, which is the baseline, the Maya constant, and Maya Gaussian sinusoidal scenario, all these three scenarios consume less power than the scenario where there is absolutely no security against power leakage. So where there is no baseline, no Maya, nothing. Okay. Now, why is this happening? This is happening because of use of idle thread, right? You're trying to use idle thread, and that will actually reduce the power on an average. And the exact numbers are 35%, 41%, and 29% for the three scenarios. Now we look at execution time. So the y-axis is the normalized execution time or the normalized duration, and the x-axis is the different applications. So we see that there's an average slowdown of 63% in the noisy scenario. There's a slowdown of 100% when we're using Maya constant, and there's a slowdown of 50% when we are using a Gaussian sinusoidal mask. Now, the slowdown in case of Gaussian sinusoidal mask is less as compared to the other two scenarios, namely because it allows the application to also run at high power, right? I mean, there can be scenarios, there can be like the Gaussian sinusoidal mask allows the application to also execute at high power, which will actually reduce the execution time. So to sum up, the slowdown in Gaussian sinusoidal case is only 50%, which is the smallest in as compared to the other two scenarios, which is the noisy baseline and the constant. So we have come to the end of the discussion. I'm just summarizing the presentation. So we discussed that Maya consists of a matrix-based controller and a mask generator. We looked at how the mask generator should satisfy some requirements and why we should use a Gaussian sinusoidal mask. Finally, we evaluated Maya using ML techniques, and we found that the accuracy drops to 13% in the non-adaptive scenario and 20% in the adaptive scenario, as compared to 92% in the scenario where there is no Maya. The average power consumed is 29% lower, which is again a victory for Maya. But the average execution time is 50% more as compared to the execution time of a scenario where you don't use Maya at all. Now, the big wins are that it can be implemented on software, and power reshaping also protects from other physical side channels like temperature and EM. So these are some points for discussion. Thank you. We can take questions.
Yeah, so the 50% performance drop is actually a huge drop.
That's true. Yeah, but it is less than compared to the noisy baseline or the constant scenario. So it's like an improvement, though it might not be a great number.
Sorry, what is it is normalized to?
So it is normalized to the scenario where there is absolutely no security against.
Yeah, it's the baseline. It's the baseline with no Maya, right?
Yes, yes.
Okay, so lower the better, right? It's the
Lower
execution
the
time.
better. Yes. So what I was trying to say is that the other baseline, which is the noisy baseline.
Aha, got it, got it. Yeah, yeah, yeah. So overall, it's not a big deal actually.
Yes.
Okay. Others, any questions? Okay, so if there are no questions, we can move on to the next presentation. It was a good one. So Sai, are you ready?
Yes, sir. Try sharing the screen. Is it visible now?
Yeah, 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 yeah. Finally, yes. Go on.
Okay. Yeah, so hello everyone. Today I will be presenting about the paper cage telepathy. So leveraging a shared resources attack to learn the deep neural network architecture. So yeah, this is the outline. We'll be going to introduction, 10K feet overview of the attack, background, how the matrix multiplication takes place, algorithm, evaluation setup, how the matrix parameters get extracted,
It's
results.
okay. You go on. There is no need to
Yeah,
read all this.
yes, yes. Yeah, so coming to introduction, many companies nowadays like Google, Amazon are providing MLS service for training of these deep learning models and later deploying them using their APIs. So, but most of the, I mean, the companies mostly use a particular toolkit. Uh, I mean, all these companies use a toolkit which is specially optimized for matrix multiplication, which is open source, which is the OpenBLAS or Intel MKL libraries, which implement this generalized matrix multiplication for all the different matrix multiplication that the deep neural networks require. But it has been analyzed by the authors that this generalized matrix multiplication is vulnerable to cache-based side channel attacks, and we'll be leveraging this insight and we'll be attacking using this information and finally getting the the deep neural network architecture values. Yeah, so this is the overview of the
What do you
attack.
mean by deep neural network architecture values?
Yeah, I will be explaining in the coming slides, sir, about the deep neural network and their what the architecture comprises of.
Okay, okay.
Yeah. So basically, deep neural network architecture comprises of different things like layers. By layers, I mean there are convolutional layers, fully connected layers, recurrent layers. So and for each layer, they also have the number of neurons, right? So these are the values which we are trying to obtain using this attack, which I'll be discussing further. But yeah, coming to the overview. So basically, we have the deep neural network architecture, which we want to, retrieve values which we want to retrieve. So to compute the values, we generally perform a huge matrix multiplication. But we have already seen from the previous insight that all these matrix multiplication involves an algorithm which is vulnerable to cache side channel attacks. So by attacking the cache using the cache side channel attacks, we'll be retrieving the values of the matrix, and we'll be seeing how this matrix value can be translated to the deep neural network architecture values. Yeah, so coming to a deep neural network, so deep neural networks are nothing but a stack of different nonlinear units which are used for feature extraction and thereby for predicting output. So these are the two different neural networks which we will be looking in this attack. One is the VGG16 architecture and other is the ResNet 50 architecture. Yeah, so coming to what comprises of the deep neural network architecture. So there are different types of layers, like I previously said, like fully connected layer, recurrent layers, convolutional layers. But since we will be discussing only two different types of neural networks, we will be limiting the types of layer. And inside the layers, there are different hyperparameters, which we'll be seeing in the upcoming slides. And there are also activation functions. Activation functions are nothing but for activating a set of neurons for learning the complex patterns. Yeah, so coming to the very first type of layer, the fully connected layer. So fully connected layer is nothing but where every neuron is connected to each other through edge. The edge compresses of weight. So if we think this neural network in terms of matrices, this the second picture is the one which we'll be obtaining, where one input data is m equal to 1, and the weights in the edges will form the weight matrix, and we'll be finally getting the output value. And this is for one data point. If we take like batch of data points, we'll be getting m different data points, and this will be the the matrix multiplication block diagram. And if we get the matrix parameters, like for example the letter A is the input matrix. So if we see the number of rows and number of columns are m and k, similarly for the other matrices. So we are looking into this because we'll be later using this matrices value to map to the DNN architecture values. So for example, if we see here, this the number of layers in this deep neural network is 1. So so the number of matrix multiplications, suppose if there are two different layers, we'll be having two different matrix multiplications. So this is how we'll be like converting the matrix parameters into the hyperparameters of the DNN architecture. So for the fully connected neural network, the number of layers corresponds to the number of matrix multiplication, and similarly the number of neurons at a particular layer corresponds to the number of rows for that matrix. Here theta is nothing but the weight matrix. Yeah, and similarly the next type of layer is the convolution layer. Convolution layer is nothing but it is used in images classification. Mostly it is used for feature extraction of images. So as you can see in the GIF, it uses a filter to extract the features from the input data. So basically the figure 2 is how most the mostly the algorithm is being implemented. So if there are DI different filters, they're kind of cascaded into different columns, and the input, which is 3-dimensional, is formed as a 2-dimensional matrix. So basically the takeaway is similar to the previous slide which we have seen for the fully connected layer. For the convolutional layer, we can map the hyperparameters to the matrices values as follows: the number of the convolution layer, the filters, the number of filters being used, filter size, and the padding. Padding is useful because if the filter wants to, if we don't have enough input data and we want the filter size is more than the input data, we want to add an extra 0 data for the input. Yeah, so coming to the final layer, the pooling layer. The pooling layer is always used in between two different convolutional layers. It is further used to reduce the the
You got
dimensions.
disconnected.
Hello.
Yeah. Okay. Go on.
Hello, sir. Am I audible?
Yeah. Yeah. Go on.
Yeah. Okay. Yeah. And coming to the final layer, the pooling layer. So it is also used for the reducing the dimensions of the feature. As you can see from the GIF, there is a particular type of pooling operation called max pooling, which select the maximum value. And similarly, the hyperparameter here is nothing but the pool width and size, which will be mapped to that corresponding matrix column values as seen in this table. And finally, coming to the activation functions, the neural network generally uses nonlinear activation functions like ReLU, TANH, and all. So to differentiate between the different activation function, ReLU is a simple function which is a max of two different value. So they basically monitor this libm library to make sure whether that particular the architecture uses ReLU or it uses a different activation function. And they have concluded that most of the neural networks uses ReLU as ReLU or its variants as activation function. Yeah, now we have till now we have looked how we are mapping the DNN architecture values to matrix parameters. Now we'll be looking how the matrix multiplication takes place and how we can leverage this matrix multiplication and do a side channel attack. So basically there are these two different buffers, buffer A and buffer B, where the final matrix multiplication takes place, and they have their respective size PQ and QR. But we have already seen our matrices are not of that same size. So what we basically do is we try to reduce their basically try to reduce the size of a matrix by implementing what you call the loop, by writing a loop structure. So the m cross k and k cross n will be written in will be looped together to finally finally place them into this buffer A. So initially the n got reduced to r, and the size the values k got reduced to q, and then the size m got reduced to p. So now we have our required size values. So what we do is we basically loop over these values and place them inside this buffer, and in this buffer the particular matrix multiplication takes place. And this is the overall algorithm which is being done. It is a 3-loop process where as discussed previously, the matrix sizes are reduced so that they can be fit inside the buffer. So as discussed previously, we are using an open source implementation of this matrix multiplication. So we already know the P, Q, R, and 3 unroll values, which are the block sizes for used in the caches. So if it can, the values can be are either known or they can be reverse engineered because it is an open source implementation. So what we are looking is we want to find the values of MKN, which are nothing but the matrix
Yeah, when you
parameters.
say the values can be known because of open source implementation, what values?
So the blocks is PQ and R. In the previous slide, we have seen that we are trying to fit the matrix values.
That will be dependent on the model, right? Based on the input data, no?
No, sir. They said
That's what the algorithm says. The input is PQR.
no, sir. But they have given these values for a double data type. So basically, for a particular what is called a library, they said the value, I mean this algorithm is optimized for this matrix multiplication, and their values can be, I mean their values are predetermined or can be reverse engineered, is what they said in the paper.
So but then you can't run this library for different values. So every time you have to use with the constant values of PQR.
Yes, sir. I mean this algorithm is like predetermined. We are only providing the matrices A, B, and C, and PQR for a particular data type are already determined.
Okay. Mhm. So basically, you are providing the matrices ABC, but from this open blast perspective, PQR are already optimized, and these are the values. Is
Yeah.
that correct? Okay.
Yes, exactly, sir. So So basically the PQR are optimized in such a way that matrix A can be fit into the L2 case and matrix B can be
Got it,
fit
got it.
into. Yeah, so this is the overall algorithm of this matrix multiplication process. And what they're doing is they are basically, since this is an open source implementation, they have basically they have done a binary analysis of it, and they found a following a dynamic call graph. And this graph is nothing but obtained from the previous algorithm. And if we can see here, this graph will be executed iter1 into iter2 times, where iter1 and iter2 are nothing but the number of times the loop 1 and loop 2 of the algorithm respectively. So if we see here in this dynamic graph, if we want to if we want to find the value of iter4, we can basically probe the on copy and kernel functions, which gives us the iter4 value. And similarly, if we probe the it copy and kernel functions, we'll be getting the iter3 values. In the later slide, we'll be looking why we are doing this, because we need this iter count values to get the final matrix dimensions. Yeah, so this is the side channel attack they have basically performed to get the the iter3 and iter4 values, which we have seen in the previous slide. So basically they are monitoring the functions for every 2k cycles, and they are considering two different side channel attacks. One is flush and reload, and another is prime and probe. For the flush and reload, they are considering a cache hit only if it is less than 75 cycles. And basically the takeaway from this slide is the it copy is being called 3 different times, and the on copy function is called 11 different times. And based on it, we have already seen their corresponding the iteration count values, I mean the mapping of the count values in the previous slide. So they are on copy is associated with iter4, and it copy is associated with iter3 minus 1. So we'll be using these values in the upcoming slides to get the matrix dimension. Similarly for prime and probe.
Hey, Sai, can you tell me the threat model here? Like, what is the capability of the attacker? Like, who is the attacker here?
So for this slide, sir, or the overall attack you want?
No, for this particular slide. So you started with the notion of cloud and machine learning as a service, right?
Yes, sir.
So in that context, where is the attacker running?
So basically, this is one of the limitation of the paper, which I was thinking of explaining at the very last. They said we can implement this attack in a cloud-based system, but they haven't provided any such result, and they have provided results for in their local machine itself. They're not able. I mean, they didn't provide any result for cloud system. So
That's okay, but for flush and reload, this is a shared memory attack, right? The
yes, sir,
attackers will
exactly.
be sharing with some other processes.
Yes, sir,
So that's
exactly.
why I was asking, what's the threat model here? So that's not explained in the paper. That's what you're saying.
So basically what they are doing is they are performing all these attacks in their local machine itself. They're not using
I got
cloud.
it, man. But
Okay.
even in the local machine, there should be a notion of attacker process and victim process, right? Or
Yes.
they know everything be based on reverse engineering. They know the addresses and they are just trying to find out the latency difference.
Yes, sir. They basically, since it's an open source implementation, they already have all the, I mean, they basically probing these it copy and on copy function. They already know the addresses of it. So
Ah,
basically,
okay. So then it's a valid threat model even for cloud systems, right? Since it's an open source implementation, anyone can. So let's say I am using a cloud machine, which is, let's say, provided by Google, right?
yes, sir.
I can run it and find out the addresses of interest because anyway it's an open source implementation, right? I know the access patterns and the kind of control flow, data flow it has, right?
Yes, sir, true, sir. But flush and reload doesn't work in, we already know in cloud because it disables page duplication. And for prime and probe, yeah.
Those things are there, but prime and probe you can do easily.
Yeah, coming to, I was coming to this. So basically, there is a noise associated with prime and probe.
Obviously.
Yeah.
But it's still possible.
Yeah, it is still possible. And yeah, we'll be looking later into the results and the final result, and we'll be seeing that there is some limitations of using prime and probe compared to flush and reload.
Obviously.
Yeah. So shall I continue?
Yeah.
Yeah. Okay. So yeah. So this is for a flush and reload. And coming to prime and probe, similarly here also they are monitoring for every 2K cycles, and they are considering cache miss here for the prime and probe case as essentially, and they are considering cache miss only if it is greater than 500 cycles. And they, since they already know the, since the algorithm is open source, they have already, to eliminate noise, what they are considering is basically any cluster which have low number of cache misses. Like if we see in the interval 4000 to 6000, there are some cache misses for it copy, but they are not considering it as the valid values, so they are ignoring such noises. So that is basically how we are obtaining the iteration 4 and iteration 3 values respectively. So now we'll be looking at the execution of the matrix multiplication algorithm and how we can obtain the matrix parameters based on all the previous values which I have seen. So we have seen already in the algorithm that there are 3 different loops: loop 1, loop 2, loop 3. And loop 1 basically, I mean, this is basically a trace of 5 different iterations of the algorithm. So the the matrix multiplication algorithm does a special operation at the very last iteration. If you can see, it is labeled as number 1. So what it basically does is, if the block size is less than capital R, it divides the last iteration into two different iterations, each of equal size. So based on this value, based on this insight, they are figuring out the values of the different matrices. So since the very last iteration has a small block size compared to the previous iterations, they're making an assumption that the execution time of small blocks at the last iteration, which is indicated as t small, is directly proportional to its size. And based on it, they're calculating the following formulas. They're using the following formulas to get the matrices. So I'll be explaining for the how we obtain the value m at a high level. So if we see that, if we see in loop 3, which is basically the one which is dividing the the dimension p into values, sorry, the dimension m into block size is p. And the last iteration contains p plus m mod p size. So what they're doing is, uh, for the last 2 iteration, they're considering p as the size. Except for the last 2 iteration, they are considering p as their size. And for the last 2 iteration, what they are doing is they are getting the time value, the execution time of the last iteration divided by execution time of the normal block, which is nothing but time taken for p block. So to get the time, they're obviously probing those instructions which you have seen previously. So that's how they are getting the matrix dimension m. Similarly, for loop 2, they're using the similar technique and they'll be getting k. And similarly, for using loop 1 data, they'll be getting the value n. So once we have these values, we can map it to the DNN architecture, and hence we can retrieve the model. So this is the evaluation setup.
So Sai, one more question. So finally, the goal of this paper is to find out the size of matrices.
Yes, so the architecture, basically the what is the,
architecture is a technical word,
yeah,
but for
yes,
a high
sir.
school student, it's just the size of matrices, right?
Yes, sir, exactly.
but it won't be able to tell you the addresses from where these matrices are initialized or accessed. It just says the size of matrix.
Yes, sir, exactly.
Okay.
Yeah, and yeah, coming to evaluation setup, so they have set up a local machine for executing on the following attack. We can see as follows. They're using 4-core Intel 8 GB memory, and they're using 3 different caches, and last level cache has 8 MB size. So they're I mean, from the cache side channel attacks, we'll be getting an estimated value of matrix parameters. So to get the final value, they are assuming the following data. So for fully connected layer, they're assuming the number of neurons is basically power of 2, which is generally true in case when we try to develop models as well. Similarly, for the convolutional layer as well, they're considering number of filters as multiples of 64, and similarly for filter size. So yeah, so this is one of the result for extracting the matrix dimension M using the flush and reload in their local machine, not in the cloud. So the red circle indicates the actual value at that particular layer, and the black bar indicates the detected value or the value obtained through the side channel attack. And based on the detected value and the assumptions we have seen previously, we are deducing the final values for the particular layer, and it is indicated as a dark blue circle. This is for flush and reload. And similarly for the case of prime and probe, since there is a noise associated with prime and probe, we'll be having a the detected values will be more bigger compared to flush and reload, which doesn't have much noise. Yeah, so coming to the final result, so all these architectures contains millions of parameters. Like we have seen the number of neurons, and combining all those values, they will be in the range of 10 power 46 for ResNet, and 10 power 12 for VGG16. So using this cache side channel attack, we are able to bring down the architecture size to around hundreds to thousands for ResNet, and in terms of 10 for VGG16. And similarly using a prime and probe as well. So OpenBlast and MKL are two different open source libraries which implement the matrix multiplication. So the reason we are seeing higher value for the prime and probe for MKL libraries, because the ResNet have smaller matrix dimensions for when we are trying to when we are trying to do the matrix multiplication. And MKL handles the small dimension in a special way. Like take analogy of tim sort. Like a tim sort, if size is small, it uses insertion sort, right? So similarly MKL uses one of a technique if a matrix dimension is small, and that's the reason if when the attack is performed, the architecture space is still pretty high.
Yeah, I didn't get here. So 10 to the power 46 is a huge number.
Yes, sir, because
And
they are
how
considering the
come
number
it
of
becomes?
neurons, filter sizes, and all the values.
Uh-huh. And
Yes, sir.
now it has reduced to 512. So what are the things that we know now because of which it reduced
Yeah,
exponentially?
we know the number of neurons, the number of filters which are being used at each layers, the filter sizes, the pool size, and the stride size. So basically, the sizes are nothing but the size of matrix, right? So
Uh-huh.
yeah, so that's the reason. So that's the reason
Got
the
it, got it.
the matrix multiplication is was vulnerable to this cache attack, and we were able to reduce to such small number. Yeah, so coming to conclusion, yeah, so we have already like inferred the matrix multiplication in ML algorithm is vulnerable to cache-based side channel attacks, and using one of side channel attack, we can obtain the DNN architecture by mapping the matrix parameters to respect to DNN parameters. And yeah, so these are the limitations that we thought of. So current attack basically works because it is an open source implementation. So for example, if the cloud service uses a proprietary implementation of their own with high performance, we will be having issue with this following attack. We need to develop a new attack altogether. Flush and reload can't be used in cloud services because it doesn't allow page duplication. Similarly, if a matrix size is smaller than the block sizes are nothing but PQR and different values. So as we can see in the result slide, if the matrix size is small, the open source libraries implement a different algorithm altogether, and we won't be able to reduce the search space. We'll be like need to use a different use an adaptive kind of attack for it to know when the matrix size is small and matrix size is high. And similarly, and final limitation is they didn't provide any like results for cloud system. They basically provided results for their local machine itself. But based on discussion, I think prime and probe still works for the cloud service. And thank you. And any questions?
Yeah, questions, others? I'm not sure whether others are listening.
Okay.
Anyway, it was a good presentation.
Thank you, sir.
I had a question.
Yes, please go.
Yeah,
There
for
are
that
questions
number
from
of
Visi. Yeah,
parameters,
go on.
for the number of parameters, I did not understand what is that large number actually denoting. Is it just the size? Is it just the information like the matrix sizes and things like that, or is it also the values of the parameters of the neural network?
So basically, we have already known the block sizes, right? Since it is an open source implementation of algorithm. So, for example, in the DNN, while they're building the DNN architecture, if they're using a smaller number of neurons at initial layer, and then they're using more number of neurons for a better learning and better for improving the accuracy. So at the initial stage, since there are small low number of neurons, we have already seen in the very first slide, the number of neurons depends on the matrix size. So
Yes.
yeah, so if since the matrix size is small, and if it is smaller than the block size that is already implemented in the open source library, the open source uses a different algorithm altogether, and this attack will fail for that particular layer. So that's the reason we are having like a higher value for such space.
Okay. Okay.
So, any comment on the number of layers, the actual number of layers in these networks?
Yes, sir. I mean, the values here, the VGG 16 indicates the number of layers, and in ResNet 50 indicates the number of layers.
Okay, okay. So for 16 layers, you are having this large number of the search space slide that you had.
Yes, sir.
It had a huge number, right?
Yes, sir. 5 into 10 power 12 compared to 50 layers, which has 10 power 46.
Yeah, yeah, that explains.
Yes, sir.
Okay.
Sai, I have a question.
Yes.
So you mentioned about some variables PQR, and you
Yes.
said those the size, and you mentioned something about the cache size and these values. What was it exactly? And there was some assumption related to these three variables, right?
Yeah, exactly. So basically, when they are implementing this open source algorithm, they have highly optimized for caches, and they have like, I didn't go through the algorithm end to end, but based on what I have read, they have choose this PQR value such that it will be the matrix multiplication that will be done will be highly optimized for the multi-level cache hierarchy. So that's how they got these values. They choose these values more like.
Yeah.
And if these values are not available, they said the authors have concluded that since it's an open source, we can try to reverse implement and reverse engineer and get its values.
Yeah,
Yeah,
if I may add, like these values, like for example, P, this value is set so that it fits the L2, and for R, the value is so that it fits the L3, so that the calculation gets optimized.
Yeah.
Actually, my point is that does it have anything to do with the efficiency of the attack? I mean, whether changing these values or if the PQR values are larger than what they have taken. So will it impact the efficiency of the attack or the kind of data or whatever data they have, they are able to extract?
Yeah, so basically we have seen in the final results, right? So if the matrix size is less than the block size, they use a different algorithm altogether. Like I have given an analogy of tim sort, right? For example, if data size is small, it kind of uses insertion sort, and if data size is large, it kind of uses quick sort for partition and all. So as far as I have read, these open source library also kind of do similar thing. If the matrix sizes are small compared to the block sizes, which are PQR, which you are saying you want to increase, right? So if you increase it, they will be using a different algorithm, and it may also impact the performance because they have optimized these values for the cache. So that's
Okay,
what
so you
I'm.
mean that irrespective of the values of PQR, the vulnerability still exists and the implementation of the algorithm will vary depending on the values for
Yeah,
these
I mean,
PQR.
we can able to reduce the search space at least till an extent, even if we are not able to completely bring down to, let's say, hundreds or thousands.
Okay,
Yeah.
okay, thank you.
Okay then, done. Devasis, you need to stop the recording. Is it done? Is Devasis there?
Yes, I'm here.
So are you done?